study surfaces of other dimensional objects.
Okay. So essentially the Euler characteristic is going to be a formula. Okay? So it's going to be a formula. We have a formula up there so you don't have to memorize it, you can write it down with your notes. So in any sphere or any polyhedron, which is essentially a sphere cut into faces and shapes, so you have the number of vertices minus the number of edges plus the number of faces is going to equal 2 every time without change. So how do we prove that? Because you're not going to believe me. So we have that sphere up there. I'll draw it. Okay. So looking at the sphere, we're going to count the number of vertices starting there. So vertices equals 2. Pretty easy, 1, 2. For edges, spheres don't really have edges, but you can bear with me on this. We have 1, 2 for edges. And for faces, we have the northern and southern hemisphere of the sphere. So faces is also 2. Whoops. Okay. So when you put this on the formula, it's a pretty easy math problem. These cancel out, you get 2. Wow. Okay. So that's not really enough to prove anything to you, so we'll step it up a little bit. I know you're worried. So we'll add 2 more vertices here and here. Connect those. And then add 4 vertices there and there. And now we're going to count and do it again. So we have 1, 2, 3, 5, 6 vertices. For edges, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And then for faces, we have the northern and southern hemispheres each cut into 4. So we have 8 total faces. Put that into the formula. So you have 6 times 12 plus 8. This goes to negative 6 plus 2, or plus 8, I'm sorry. I'm getting ahead of myself. It's 2. Oh, okay. So,
the true question is everything 2? The answer is no. Only spheres, which are polyhedrons, are 2. Everything else can be characterized by a formula 2 minus 2g. G being the number of holes there is in the object. This is only for 3-dimensional closed orientated things. So for a sphere, you would do the formula 2 minus 2g. G would be 0 because there are no holes, so 2 minus 2. 2 minus 0 is 2. The Euler characteristic is 2. For a torus, which is something like a donut, you would do 2 minus 2, and that would give you 0. Same thing for a double, 2 minus 4 would give you negative 2. A Kime bottle, which is something that interlocks, it's kind of weird, is also 2 minus 2, giving you 0 just like the torus.
If you want to learn about Kime bottles, ask Professor Nimershiem.
He has a necklace, that's pretty cool. So the one thing we had trouble with was what do we do with this? So Luke is going to show you what you can actually do with these numbers.
Okay. So I know you've all been wondering how many hexagons and how many pentagons are on a soccer ball. Some of you may know because of this, but I'm sure none of you have ever counted because it's awful to try and count. So we're going to set it up like this. Essentially, we're going to assign the variables p and h to the pentagons and the hexagons respectively. So for faces, it's pretty easy because you're just counting them all up. So it's going to be p plus h. So vertices and edges get a little bit more complicated. So we'll start with edges. As you can see, every pentagon and every hexagon has 5 and 6 respectively. But you're counting everything twice if you're going to do 5p plus 6h. So you have to kind of compensate for your overcounting. If you could tell, every edge is going to be counted 2 times because it's contacted by 1 hexagon and 1 hexagon, or 1 hexagon, 1 pentagon. There. So you divide that whole formula by 2, and you get the number of edges. Vertices the same way. Every vertex is going to be counted 5 and 6 times respectively. But you need to divide it by 3 because it's being contacted by 2 hexagons and 1 pentagon every time. So you divide that and put it all into the formula. Well, that was good on time. So essentially, I did the math, so you didn't have to. What we're going to be doing is taking the whole top formula times 6, get rid of the denominators, add and subtract, and you're going to end up canceling out all of your hexagons and end up with p equals 12. So on every standard size 5 soccer ball, there's going to be 12 pentagons.
Woo!
Question? Ooh, we have a question.
Well, what about the hexagons?
Oh, I'm glad you asked. So every pentagon has 5 sides and it's surrounded completely by hexagons. So take 5 times 12 and you get 60. So that's also overcounting because there's obviously not 60 of anything on this. So what happens? Well, every hexagon is surrounded by 3 pentagons, so you count everything 3 times. So Michelle, What's 60 divided by 3?
20.
Yeah! So every standard size 5 soccer ball has 12 pentagons and 20 hexagons.